Hello, and welcome to the STEM Brothers podcast. I'm Quasi Vincent.
And I'm Basir Vincent.
And we are the STEM Brothers. So, welcome back, or hello for the first time. We're on episode 4 of the STEM Brothers podcast. Can you believe it, Basir? We got 4 of these done.
That's 4. Hopefully the sound's a little bit better on this one. I just actually got a mic.
Yeah. It sounds good on my end, so hopefully the listeners can hear the improved sound quality as we're both speaking through mics. Let's get right into it because we have a great guest today, and I wanted to not spend so much time on our intro so that we can get to the guest. But one of the things that I like to do at the top of our shows is, if you are someone who's being introduced to the show for the first time, if this is the first episode you're listening to, or if you've listened to the previous ones and you're still trying to figure out, okay, what are these guys up to? I was looking at this website, this YouTube channel called AfterBuzz TV. Have you ever heard of this, Basir?
Yes, they do talk shows after Breaking Bad, right?
After Breaking Bad, after Arrow, after all the big television shows, they do a whole thing. So and then AMC has their own Talking Dead show that they run after the Walking Dead, and it literally all these shows are podcasts and talk shows analyzing the television show that they're based off of. So they go behind the scenes, they talk to the writers, they speculate on future storylines, etc., etc. And it got me thinking, just think about how all that time invested in breaking down these TV shows. What if we could find a way to, in a fun and interesting way, break down science, technology, engineering, and mathematics the same way? Because really, those things impacting science, technology, engineering, and math, or even better said than that, science, technology, engineering, and math impacts things that we interact with on a day-to-day basis. So there is nothing more important in my mind to talk about regularly than STEM, than science, technology, engineering, and math. That is the goal of the show. If you want further information and would like us to come out and do a presentation for your class or your group of students or young people, you have a program at your college or university you'd like us to speak at, we'd love to do it. Please shoot us an email at stembros@gmail.com. That's stembros@gmail.com. And you can also check out the website. Basir, what's the website URL?
The website is stembros.com. So that's stembros, stembros.com.
Absolutely. So with that said, let's get into today's show and the topic of this episode. Me and Basir found a very interesting article that really prompted us to cover what we're covering on today's show and to find a guest like we found. And really, we really couldn't find any better guest than the one that we got to talk about the subject matter that we're going to cover today. First, let's talk about the article that we found, Basir, that was just super intriguing. And when you read the headline of the article, right away, you can't help but to your ears can't help but to perk up and be extremely intrigued by what the implications of this kind of work might be in the future. So, just to give you an idea, the title of the article that we found, and this was on CNN's website, so this is a CNN story. Give them credit. The title of this story is "Scientists Grow Monkey Limbs in the Lab." that's mind blown, right? It sounds like something out of a science fiction movie, but this is something that's actually happening. And the relevance of this is that what they're doing, what's happening is that there's a research organization that is based out of the Massachusetts General Hospital Center for Regenerative Medicine, and it's the Ott Laboratory for Organ Engineering and Regeneration. And what they're doing, what the folks at this research institution are doing, they are working on regenerating the cells of a monkey arm, and more specifically, what they're doing is they are taking a look at, or not taking a look at, excuse me, they're actually doing the work of learning how on the cellular and molecular level to stimulate the generation of blood cells, muscle cells, all the different types of cells. And they're they're regenerating these cells around essentially what's a carcass of a monkey arm. They call it a scaffold. So it's a arm from a monkey that's been expired, and they take this scaffold, so this carcass of the arm, which has no living cells on it, and they introduce living cells from another monkey and then try to grow the cells that monkey has, that the live monkey has, that make up that live monkey. So in other words, one of the big problems with organ donation and things like that is that you have to find a match. You have to find blood type matches, different things like that, different issues, or otherwise there could be rejection. The body rejects these foreign bodies being introduced to it. So what the science is doing now is saying, hey, listen, what we can do is we can recreate essentially the molecular makeup, the cellular makeup of someone who needs a limb or organ. We can recreate their cellular makeup on top of the carcass or the scaffold of a donor who may not necessarily have matched up, who does not match up with them on a cellular molecular level. So they strip the limb or the organ of the cells that the previous owner of the limb or organ had. And this is this as you'll find out, this work is still a long way from being completed, but they're making advances by leaps and bounds here. But basically they take this carcass, this shell, and they grow the necessary organ, they grow the necessary cells on top of this body part, and this way the cells match that of the person needing the organ or the body part donation. So it's pretty amazing, pretty advanced stuff, but it's happening. And obviously, as we know from other types of scientific experiments of this nature, once they're on the trials of performing these things with monkeys, given how close monkeys are in anatomy to human beings, being able to transfer this technology to us as human beings is not that far off. So if they can successfully do this with monkeys, then there's no reason why a vet coming back from the Iraq or Afghan wars who has lost their limb, why this technology years down the line cannot be used to regenerate a limb they may have lost over in battle serving the country. So there are a lot of interesting applications for this. And Basir, what were some of your thoughts and some of the things that you saw in regards to this article?
What I really liked about the article is it drew out the need, and really focus of this podcast is to understand how the STEM fields address issues. And one of the statistics that's given in the article is that over 185,000 amputations happen each year in the United States alone. And currently in the United States, 2 million people are living with an amputation. That's something that can be solved, and people are constantly working on from such a variety of different ways, and all of them have their hands somewhere within science, technology, engineering, and math. One solution that could be to this is to create something, a robotic arm or a replacement arm. But in the case of this article, it's really going into the potential of rebuilding that arm. And the field of STEM that goes into, biomedical engineering, it's a perfect example of how there are day-to-day things that are happening that just highlight how people in this field are giving back to the community.
Absolutely. And one such person is today's guest, or the guest for our episode 4. She is Dr. Tonye Briggs. She has her Ph.D. in Biomedical Engineering from the New Jersey Institute of Technology. And we had a chance to speak with her. She was generous enough to give us some of her time. And she spoke to us about a variety of issues. So we'll let you hear that interview just to give you some background on what someone who is working on this kind of science, you'll get a little sense of their background and what her thoughts are on the work that she's doing, and some of the things that someone can do who may be interested in getting into this work, some of the things they can do to pursue careers in this area. So without further ado, let's get into our conversation with Dr. Tonye Briggs. And welcome back, everybody. So, as promised, we have on the line with us Dr. Tonye Briggs. Tonye, thank you for joining the STEM Brothers podcast. How are you?
I'm great. Thank you for inviting me on the podcast.
No problem at all. So, Tonye, one of the things we wanted to do on tonight's interview is give folks a little insight about biomedical engineering, because both me and my brother have come across a lot of folks who majored in biomedical engineering, and there's a lot of variation in the field, and as with all engineering, but we wanted to speak to an expert like yourself and kind of get what your perspective is on what is biomedical engineering and what is the impact on society that folks who major in biomedical engineering have.
Yeah, well, biomedical engineering, or bioengineering in some institutions, as it's called, is a very vast field. But to break it down in simplistics, it's the intersection of engineering and biological sciences. The field that I studied was biomaterials and tissue engineering, but there are other fields like bioinstrumentation. Imaging is considered biomedical engineering in some institutions. There are other areas that are involved in rehabilitation, prosthetics. So it's a vast field, but to break it down, it's basically the intersection of medical science, biology, and applying engineering principles to it.
Okay. And so when someone says they're a biomedical engineer, what are they specifically talking about in terms of their knowledge? What that intersection that you talked about, like, are they doctors? Are they engineers? Or it sounds like they're a perfect hybrid of the two, right?
It is a hybrid, and is being in the field. the many of years I have been in, I've come across a lot of different people with different disciplines. It is an disciplinary field itself, but I've came across people that have gone through the training of a biomedical engineer and have become medical doctors. People have become researchers. I've had friends that have become that were mechanical engineers and became biomedical engineers because of their training. And a mechanical engineer was useful in determining the relationship with the structure and force to, say, like a joint bearing, like a bone or knee, so that discipline that feeds into biomedical engineering. Electrical engineers, some of them come into biomedical engineering. So you have all these places where these disciplines that can feed into biomedical engineering, and once you're in biomedical engineering, you can go out into other different disciplines. You can become a physician. You can stay as an engineer. You can use your skills as a consultant. You can. It's a very versatile field. So it's open to a lot of different people that come from different disciplines. And once you get trained in it, because there's so many different things you can learn that expound upon the engineering, but can go deeper into other areas, you can be very skilled and very versatile into other disciplines as well.
Awesome.
Does that answer your question?
Oh, yeah, absolutely. Absolutely. So when we look at your journey in particular, what first got you interested in biomedical engineering?
So my journey was maybe unique in a way, because I had thought my training was going to be, at the time when I was a little bit I think people that have come from the earlier biomedical engineering training in academia, when I was going to college in the 90s, there were a handful of schools that had biomedical engineering as an undergraduate major. It was mostly something you studied in grad school. Like I mentioned before, most people either came from different disciplines such as electrical engineering or mechanical engineering and studied biomedical engineering in grad school. But when I went in the 90s, there was a few schools that were offering as an undergraduate major. At the time, I had thought I was going to go into med school, and I thought that would be a good way to have a preparation for med school curriculum, like MCATs and the whole bit. And when I was in college, I decided that wasn't the route for me to go to med school, but I stayed with biomedical engineering as a discipline, and I stayed with it throughout my training. I thought it was a great way to get a lot of different knowledge, like a master of all trades, so to speak. I was exposed to physiology. I had as an engineer at the school I went to, which was Case Western Reserve University in Cleveland, Ohio. All engineers had a certain curriculum. So we had that on top of the biomedical engineering curriculum. So I thought that was it was very challenging, don't get me wrong. Very, very challenging, but that was a really good foundation for whatever I wanted to study later on, or whatever I wanted to do in terms of a profession. And it just turns out that I had gone through undergrad, worked, and then gone to grad school in biomedical engineering as well, which I think is a little bit unusual. Most people do graduate school, biomedical engineering grad school. So I thought that was a really good foundation for me.
Awesome. Speaking of getting into what you wanted to do, can you tell us a little about what you're doing now?
Sure. So right now I work for a cellular therapeutics manufacturing organization company. It's called PCT, and it's in North Jersey. And we are a contract development manufacturing organization, and we are specialized in immunotherapies. We work for we work with a lot of different clients, large and small, in the pharmaceutical space, and our specialties in cellular manufacturing for immunotherapy products and regenerative medicine as well. So I just started working there the past 9 months, and so I still feel somewhat new, and I am still kind of the quote-unquote new girl in my group, and I work in the process development group. So I work with a team of people, and we try to work with the clients and try to develop ways to make their process faster, more efficient, more cost effective. And it's been a great experience. And I think my training as a biomedical engineer, my title is a scientist. But my background in my training in my graduate work was in tissue regeneration and stem cell therapy. So my graduate school research, not to get too technical, was trying to regenerate bone tissue onto materials, which we call scaffolds, which is kind of like a fancy word for a sponge. So trying to manipulate stem cells into growing into bone tissue, and like us, in a smaller scale, not really like making a whole femur or anything, but like on a small scale. And so I use that knowledge with stem cell regeneration in my current job, which we're working with stem cells of a different capacity, of course, for different applications. But nonetheless, my background in biomedical engineering and specifically my graduate work was very pertinent.
So we hear a lot about stem cells in the news and things like that. For the person just kind of getting introduced to the field of science or who has been away from it for a little bit, can you refresh us a little bit, explain what a stem cell is, and kind of start by just reminding us basic biology, like what's a cell and how does the reproductive process take place in in your environment? Like, how do you make cells and manufacture them and things?
Oh, okay. Well, yeah, maybe it's a little bit misleading when I say manufacture cells, because you can't really just like make cells. Like that would be amazing. Science fiction. Or more like maybe a manipulation of cells, or processing of cells is a better term, but making cells is that's like straight science fiction stuff. That would be very, very amazing and cool and a little bit scary, but nonetheless. To break it down, a cell is basically the most basic building block of life. And so we all have trillions upon trillions of cells in our bodies. When it comes down to it, a stem cell, and it depends on the source of the stem cell, but and I've worked with different types of stem cells. When I was in graduate school, we worked with what we called, and follow me here, mesenchymal stem cell. And mesenchymal. These originate from the bone marrow.
Okay.
And adult bone marrow, any type of bone marrow per se. And these mesenchymal stem cells have the ability to turn into, the scientific word is differentiate, but turn into to bone, which is I was working on in my graduate work, and to cartilage, and to fat, and to other types of cell types, depending on what type of cues you give into their environment. And by cues, I mean, say like food. So cells feed off of, well, we call it media, but to more simply, we'll also say food. So if you give bone cells a certain food, the stem cells a certain food, they'll turn into bone cells. If you give them another type of food, they'll turn into cartilage cells. If you give them another type of food. So these different types of recipes can shift their fate, so to speak. So that was what those cells do. There's other cell types that originate from other areas of the body, like if you have hematopoietic cells, that's another long term. So these are also these are the major the progenitors or the beginners of the blood cell types. So that's what I'm working with at my job, is how do we take these blood maybe I should say grandfathers, like they're the progenitors. So they're like these grandparents to other cell types by giving them different cues, trying to direct them into a different endpoints. So trying to manipulate them and turning them into something that can help other people, or to turn it into a therapy. So that's what I'm working with now. But so stem cells are pretty much like these cells that are kind of like you can manipulate them into other cell types depending on where they came from and the type of message you give to them. Does that answer your question?
Oh yes, definitely. So looking into the future, and even what really gets you excited, or what's really the end game of some of what you're looking into now in terms of the stem cells and
what's getting me excited? There's just so much. I've been in this type of field for the past 10 years or so, and every time there's a development, it's just you never know where things can go, especially in the tissue engineering space, with a lot of people suffering from like the wounded warriors suffering from debilitating trauma, and if they blow off their leg in battle, or people like can get into accidents or things like that, and if you can essentially have a product that can replace a body part or an organ, or if you have a traumatic brain injury, which is very prevalent in not even just people that have come back from the military, or like sports players, or people that have been in car accidents. If you can help people in that capacity in the stuff that is going on in immunotherapy, people are being treated, certain cancers can be treated with different immunotherapies, and these are things that people have died of years ago, and now people have a chance to live. So the thought of either improving people's lives or extending people's lives is really motivating. That's what gets me out of bed on the days I don't want to get out of bed. It's like, oh wait, the work that I'm doing, even if it's like incremental on a day-to-day basis, can potentially impact someone's life down the road. And so that is really a great motivator for me. So, and it's really exciting, and there's a lot of work going on, and people are working really hard to make these things happen. And so it's very cutting edge and very cool.
Wow. Can you say how far away we are from sort of some of the things that you talked about? Let's say that someone loses a limb, and how far away are we from either giving? Go ahead.
Yeah. I mean, it depends, because there's a lot of different moving parts to these type of things. You have the technology itself, which I feel like sometimes it can go really, really slow, and there'll be like a game changer, and things will move fast, and then it'll be slow again. It's the short amount of time. I think my career has been short but long at the same time. It's weird to explain, but I feel like the short amount of time I've seen is like there'll be a great breakthrough, and then it'll be a stall, and there'll be another great breakthrough, and there'll be a stall. And there's other things that are out of the control of research in terms of the regulatory space, the FDA. You also have to think about insurance, the reimbursement whole thing. And so there's a lot of moving parts besides the technology and the research, which is very challenging in and of itself. But I think that things can grow, and I have the hope that things can be exponential in growth, and there'll be a lag, and depending on how research is being funded in this country and internationally, and the pipeline of talent coming in, that's another factor as well. If you don't have the talent to feed into the pipeline, if you don't have the money to fund the research, then there's going to be a lag, and that's just the matter of fact of it all. There is privately funded companies or publicly funded companies that do research, but most of them they need a profit, and if the profit is not, if you don't have a profit making business, then they're not going to keep on going with the research. So I think it's important that universities and other institutions are doing this innovation. But in terms of years, I mean, I wish I had a crystal ball, but I would say we're probably a few decades away from some of the things. Some of the things are like an artificial bladder, I think, has been done at I want to say Anthony Atala has been working on that. I don't know if that's like on the market or if that's late stage development. So there's some things that are out there, but
what was that last thing you mentioned? Artificial. What was it?
There's a researcher at Wake Forest. He does a lot of regenerative medicine work, and I think he's come along with like a bladder.
Bladder. Okay.
I could be wrong.
Awesome.
He's out of Wake Forest.
Okay.
Awesome. But I have to double check that. I don't want to get the wrong information.
No.
But yeah, there's work. It's just it's coming along, but there's definitely a lot of innovation, and there's things that like we don't even think about that there's like a lot of work on. Like, there's a whole other world of stuff that's going on that is not very obvious to society, but is definitely in development. So
absolutely,
those things are like nanos, particles, nanoscience, nanotechnology. Sometimes you don't see the obvious implications in health and science, but there's been a lot of work there that's going to come along and make a difference sometime soon.
Got you.
That's an excellent look into the future. Just to switch it, let's kind of look into pulling from your past and really wanted you to talk to our audience. So any young men and women that are getting interested in potential fields, what advice would you give them, or kind of what paths are there? You mentioned a little bit about other engineerings crossing over, but what suggestions would you give?
What suggestions to get into biomedical engineering or to any engineering?
Let's start with just to get into biomedical engineering, but really just to get into your field, because like you said, you're now a scientist. You work with mechanical engineers, you work with chemical engineers. Right. So just really getting into the field. What?
Right. Well, I think the foundation, as I don't want to say boring, but like as standard as that is, that you can't get away from it. Just having that foundation of the core curriculum for engineering in college, and where I went to school, it was 3 semesters of physics, 4 semesters of math. Those are the ones that stuck out to me, but I think that's really essential just to build your foundation, just to build your skills. I think every engineer needs those tools. That's something that you just cannot avoid. So if you're a high school student, just boning up on your science and math, those are things you just can't walk around as an engineer. And that's something I kind of wish I was a little bit stronger in, and I wish I going back, I wish I was a stronger mathematician, and I think that would have helped me in some areas. But yeah, and there's so many more resources now than there were when I was going to college and in high school even. So there's so many areas, so many resources where if you want to improve on math skills or science skills or chemistry or mechanical engineering or physics, there's resources online that are free if you don't have the funds to have a private tutor. I suggest the Khan Academy, KHAN. The last time I checked, I think they have free lessons online for, and this is not an endorsement or anything. This is just a suggestion. If for you don't even have to be a high school student. You can be a college student, and like they have videos online for calculus and statistics and physics and chemistry. So doing AP courses, I think that's a really good way to bone up on your curriculum and not have to take a course in college. So I looking back, I took AP biology in high school, so I didn't have to take biology 1 as a college freshman, which not only, frees up your college schedule, but it saves you money. If you don't have to take a course, that's one less course you have to take. So, it's just the essentials, and it's maybe it sounds boring to say you can just take these courses or take the AP course. I think they still have the AP system, if I'm not mistaken, advanced placement.
Yes,
Is
absolutely.
That still happening?
Yes. Yep.
Okay. I know this SAT's changed and all that in the last 15 to 20 years, but I think if you have the opportunity to take the AP courses, take them so you can either, have that foundation before you go to college or to test out of it. That would be great. And then when you're in college, the first couple of years, just doing the work as the engineering foundation. And then when you get past that, and then you can do the fun stuff. Then you just get through the first couple of years just with your head down, and then after that, do the fun stuff, the research, pairing up with a mentor in your program or your undergraduate major, and doing summer research. And I think that would be my advice, is to get involved with research as soon as possible, so you can see whether or not. First of all, you can see the applications to the science that you learned, the science and engineering that you've learned. Second of all, you can, if you want to go into research as a career, you can see what it's like and to see if you like it or if you don't, because some people don't like it. It's not for them. And some people do. So you can get that experience. You can also work, even if that doesn't work out as a career option, maybe you can work with a well-known researcher, put it on your resume. And maybe even work on some research that gets published, so you become be a published author, which is very appealing for if you want to stay within the same discipline or go into another discipline, or just to have it on your CV anywhere you go. It's definitely a great thing to put on your resume for any type of job. So. Yeah, that's what I would suggest, is the foundations, research, maybe work with a team. I think there's some courses now, some college courses, when you work with team projects, I think capstone projects, any type of experience that can give you that real life or hands-on, I should say, experience. Because it's one thing to learn it in a book or on a computer screen. I guess kids are learning on tablets nowadays, and maybe not in books anymore. I don't even know. Do they?
Yeah, no. The textbook industry is still out there because they're making tons of money.
Okay. I was worried. I was like, people just have iPads and Kindles. There's one thing to learn in a book, but it's another thing to apply it. So I think the application, and you can do that in college and even in high school. Not as much when I was in school, but nowadays there's so many opportunities to be part of research programs in high school or short capstone projects and things like that. So, yeah, and then after college, the world is your oyster, whether you want to pursue your career and go into grad school or work in the industry, which I suggest as well, work in the industry. And if you want to work a couple years and then go to grad school, there's no right way to set way to go about your career. That's a personal choice of what you want to do. And so
you mentioned fun stuff. So tell us something, the most fun you had either in college or early in your career.
Okay. I'll just preface this with fun being very subjective. Fun to me might be fun to different people, or not so fun to different people. But I would say productive and rewarding opportunity or experience, I should say, was when I was in, I think, my second year of working at Rutgers. I'd worked on this collaboration with this this company that was working on a product for wound healing. And so that's like, say, if you have a wound and you need some type of a bandage or some type of a dressing, and how to make that like to improve that, just so it's not just like a piece of cloth or material, but how do you deliver something that is going to expedite the wound healing process. And so I was working with different collaborators, and I was part of this team, and I was doing a lot of experiments with skin cells and how these skin cells interact with this material that was releasing a protein or technically a growth factor, and how these different formulations can improve skin cells growing. And so that was probably the most rewarding experience I had in my early career. It led to a paper that was published, and it's still getting citations, or I'm not sure if it's currently getting citations, but it was well cited, meaning that other people have gone to this paper, this research paper, and have seen the work and have acknowledged it, or citations, or cited it. So it was a chance to collaborate with a company. It was a chance to collaborate internationally because we had a scientist, researcher from a different country, Australia. It was a time for me, since I was at the time a technician, this is before I went to grad school, to feel like I was I was a productive member of a team. Because sometimes technicians, they are kind of just given the grunt work in some cases in the lab, and they're not very, I'm just saying this very generally, sometimes they're not as valued as other people in the lab. So that was a chance for me to feel like I was valued. And so I really think that was a really important piece of the puzzle in my journey in becoming a scientist engineer.
Awesome. So I know we don't have too much time left, but there were a couple really quick things I wanted to get into very quickly. But as someone who does a lot of math tutoring and math instruction, I was just curious when you had mentioned what do you think having stronger math skills, what sort of advantages would that give you in your career? And so to that lesson that we can give to the listeners, right. Why be strong in math? What kind of advantages does that allow?
Math is so essential. Yeah. I mean, like, I would say even now more than ever, if you want to go into, like, there's a field of like bioinformatics, if you want to get into algorithms, and there's just that whole world, which is I'm not really an expert in, but that is another world that has kind of opened up in the last 10 years or so. If you want to study, even if the average scientist engineer, you need to know your statistics. And even if you're not doing anything super mathy or super technical, if you're going through a research project and you need to see the difference between different experiment groups, you need to have your statistics knowledge, and what's different or not. Say if you want to see the effect of 2 or 3 different drugs, and you're giving it, you have to know the difference after you do the experiment, and you do that by statistics. There's a lot of statistics software out there, but if you don't know what it's actually doing, if you're just putting it into a black box and you're having the software spit it out to you and you're relying on the software, it's kind of, you're just kind of relying on technology, which is fine, but at the same time, it's good to have that basic statistics knowledge, if anything else. And, I can't even stress how much math is an important part of engineering, any engineering, biomedical engineering. Some people kind of like a little bit of a confession, but when I was going to school, some people kind of went to the biomedical engineering route because they thought it was going to be easier because, it's not super technical, you're a jack of all trades, and you kind of can cop out on the math part, but it's just you can never really escape it. Like it's just going to be a part of your career if you want to go to the technical research route. And even if you want to go into other areas that's not like applied science, even if you want to go into, I don't know, business or marketing. It's just essential. So you can't escape it. Even if you think that biomedical engineering is going to be easier, it's not.
Right.
Like you might like think it's okay. Like, down the road, it might not be easier. In the beginning, it might be, okay, I can probably not take as much math as other engineering disciplines, but down the road, you'll probably end up doing as much, if not more.
Right. Well, actually, Tonye, I think you hinted at it at the beginning of the conversation where we talked about the cell, right? And how you said basically human beings are made up of trillions of cells, right? So when you're talking...
billions of trillions, I mean, it's another zero on the...
Right, but a large number, right? So we're talking a large number. Right. So anytime that you're dealing with experiments and changes in cells, we're talking large numbers of pieces of information that you have to study, right, or analyze in terms of the reactions that are going on. And that's basically what bioinformatics allows us to do, right?
Well, I mean, I think bioinformatics is its own world, but like when I think of bioinformatics, I'm thinking like genes and DNA, but I mean, I think that could also be involved in it too. I'm not very familiar with that world from what I know, but it's for me, like when I think of bioinformatics, my brain automatically goes into like genes, DNA, but this is like knowledge that I've gathered through in like the last decade or so. So maybe some of the terminology is a little bit dated. Yeah. Because when sometimes you get into your own discipline, you kind of forget the other disciplines until you talk to your peers in other disciplines. It's like, oh, that's what you do? Oh, okay. Or if you go to seminars, which I suggest if you're in the academy, if you're in graduate school, if you're there for an extended period of time, I suggest going to seminars and symposiums from other disciplines so you know what everyone else is doing and not be so tunnel vision focused. I think that's what is very, very helpful. It's not required in some cases, but I think it's just good to get your head out of the sand if you're if you're in grad school for a long time, if you're a postdoc, is to expose yourself to other disciplines because you never know. And sometimes there'll be a problem and there's someone else's discipline that you may have the answer to or vice versa. So just getting a different perspective and just opening your mind is very essential. I think that was a kind of a divergence of the topic, but
not at all. But bottom line is you need those strong quantitative skills to do a lot of stuff. But it applies to your discipline. Why don't we finish off with if someone's sitting here listening to the podcast and they're like, wow, I want to make a difference in the medical field, and I always thought I would try to be a doctor or a dentist or something like that. What essentially what would you say as far as going the med school physician route versus going the biomedical engineering route? What are the pros and cons of each path of contribution to the medical field, and how would you advise someone?
And you can do both, actually. There are some people it's a small group of people that get their MD and PhDs at the same time. Mm-hmm. And if you're really motivated to go to graduate school and medical school, hats off to you. That's a very rigorous process. I know a handful of people have gone through that, so that's a possibility. But in terms of, I can't really speak about being a medical physician because I'm not one, or I haven't gone through that training. But as someone who's interacted with medical doctors, it's definitely a more of a structured route because you do have your 4 years of college and there's a certain curriculum you have to take in order to take the MCATs and go apply to medical school. I'm not really familiar with the process other than having friends that have gone through it. But there's some people that have worked a couple years and go to med school. There's nowadays, I don't think they were as prevalent when I was in school. There's post-bac programs. These are programs that are after college. So if you feel like maybe you're not as prepared after going through college, but you still want to go to medical school and you don't feel like your grades or the GPA is as strong as you'd like it to be, there's certain post-baccalaureate, I think I'm saying it, post-baccalaureate programs, post-bac programs, you can look them up, or 2-year master's programs to strengthen your CV to apply to medical school, or to take your MCATs and to apply to medical school. And medical school is, most medical schools in the U.S. are traditional 4-year training for MD, or I think there's osteopathic schools that you can get a DO, which I'm not very I can't really say what's the difference between one or the other, but you can go to a traditional medical school and get an MD. You can go to, I think, an osteopathic. I might be butchering the word. Another school, but still gets similar training, get a DO. And then after that, go through fellowship and residency and become a medical doctor and practice medicine. And you can still go into do research. I mean, I've had physicians that were my principal investigators and collaborated with on different projects. So you can still be a doctor that practices and interacts with patients, that does research. So that's a possibility. You don't even have to go through the MD PhD route. You can go through the traditional MD route and if you have time, contribute to research. So that's that. And so I'm just speaking from like someone that has observed it from my peers and colleagues. In terms of the biomedical engineering route, that also can be different for whatever you want to do. So you can go through an undergraduate program for 4 or 5 years, and then work in industry. And you can work in industry for the rest of your career and be a very successful person. What I did is I did my 4 years. I worked as a lab technician in several labs, and then I went to graduate school for my master's and my PhD. And then after that, I did my postdoctoral fellowship, and then I went to industry. And my route up until industry was a very kind of traditional academic route, but that can vary from person to person depending on your personal choices and the opportunities that are available to you at the time. So the opportunity that was available to me after I graduated was to do a postdoctoral fellowship. And so that's what I did for 3.5 years in Philadelphia at the University of Pennsylvania. And that led to, I came to, well, I knew before that my fellowship ended that I didn't want to go the professorship route. But so while I was in my postdoc program, I was making connections in industry. So I knew I wanted to go into industry eventually. So there's a lot of different paths to take. Some people become professors. I have friends that are professors that are doing well. It's challenging. And it's challenging to become a professor because you have to have funding and write grants, but it's not impossible by any means. And there's a lot of resources out there for especially unrepresentative, what's the proper term? Unrepresentative minorities in academia. I was a part of a program called the Compact Program in a graduate school, and they have annual meetings or every other year. I'm not really sure what they're doing now, but there's symposium and meetings and discussions about how to write your first grants. And that was very helpful, and how to survive your first year as an assistant professor. So there's resources out there. Like, nothing is impossible. It might be hard and difficult and challenging, but it's not impossible. You just have to be focused on where you want to go, and be also flexible, because sometimes where you think you're going to go is not where you're going to end up. So just having a vision and being flexible at the same time, which is kind of contradictory, but being prepared for that as well. So I think that's the best advice I can give, is to be prepared, have information just in case you need it. So, so some people go the professor route, the assistant professor route, and that becomes into down the line when to get tenure professor route, and can have a job for a lifetime, essentially. And some people, like I mentioned, go into industry. Some people end up in other non-traditional fields in related to science or not. Some people, some of my colleagues ended up in management consulting, so working for big firms and solving issues, solving problems of big business in that capacity. Some people go into other fields altogether. So it's about being prepared and having and the opportunity being available, and also being flexible.
Awesome. Well, Tonye, we're out of time. Thank you so much for the information. Incredibly valuable stuff there.
Thank you.
Yeah. So we will hopefully somewhere down the line be able to talk to you again and ask you some different set of questions. But this was very informative, and we look forward to speaking with you again soon.
Thank you very much. And I'm glad to talk to you guys and to share my knowledge and experience and information to whoever can gain from it.
Awesome. Thanks, Tonye.
Thank you.
And welcome back. What an incredible conversation we had with Dr. Tonye Briggs. We want to thank her for joining us on this episode. Basir, what did you think about that conversation?
I think it was awesome. Tonye is very good at giving insight into the ability for people to jump careers and gain that baseline and go into the biomedical field, even if that's not your original background, but really by focusing on strengthening your basics, you can use that later on in life. And that's a very important message.
Absolutely. Absolutely. And she covered so many different things. One of the things towards the tail end of the conversation, I want to encourage everyone to look into the field of bioinformatics. It's a growing discipline, and it really is the perfect convergence of all the various aspects of STEM. It's the convergence of computer science, mathematics, and biology. The field is growing in importance as the need to analyze and model cellular and molecular behavior and be able to make calculations and do things at a very, very high level, high volume, and rapidly, given the expanse of all the different elements that make up cells and molecules and things of that nature, DNA, all these different elements. It's just important that we have professionals who are able to statistically break these things down and model them and use computers to do that. So a great field. I encourage everyone to do some research on that, and we'll certainly try in a future episode to do an episode with a professional in the bioinformatics field, because I think it's that important that we look into that. So anyway, I want to thank Dr. Briggs again. Basir, any closing thoughts before we get out of here?
No, just always remember to look out there for the problems that need to be solved.
Absolutely. So until next time, find some great problems to solve, and we look forward to speaking with you again on the next episode of the STEM Brothers Podcast. We are gone.